Okay, today we're gonna go into chapter 15, pneumatic measurement. So we're gonna use air in metrology. So in pneumatic measurement, what we use is air pressure. So the pressurized air is forced through a port, and then we control the port size, okay? And the methods we use to measure using air pressure, we call that pneumatic gauging or air gauging, or pneumatic metrology. So again, you're going to play with the air, especially the pressure. And pressure, do not forget, pressure is your force divided by area. So therefore, the port size is very important. And we will play with that port size, okay, in this pneumatic metrology. So this method is successful because we totally eliminate the metal to metal contact. Okay, so it's totally frictionless. And it also provides power amplification along with linear amplification. So in addition, these instruments are very low in cost. And pneumatic comparators, they have power amplification. And the power for the instruments come from the external source. Okay, so the change in length signal is you can amplify that. In addition, pneumatic comparators, they're not limited to applications with air sensing. Contact type pickup elements can be also added, okay, for other measurement needs. So what it's saying is, even if this is using the air, it's not limited only to air, okay? We can add the contact type elements to the instrument. So the history, it goes all the way back to 1917. Originally, the application of this measurement was only for production inspection, okay, or gauging of the product. But they can be used to gauge several features at once. Okay, so therefore it's still an important means for production inspection today. So as mentioned before in previous chapters, language is again the least precise thing about the measurement. Okay, principles of pneumatic instruments. First thing you have to know is the back pressure instruments. So pneumatic comparators are analog, again, devices. And they use a very abundant resource, and that is your air, okay, to create change in a gauge as a part feature is measured. And they measure pressure and they measure the flow rate. The double orifice pneumatic comparator is the basis for all other pneumatic comparators. And here you can see its diagram in this picture. And the measurement we read, okay, on a pressure gauge is called back pressure gauge. And that's why we call these instruments back pressure instruments. So the air that enters the system must equal the amount, okay, that escapes through the orifice. So we call this as a double orifice system. So here you can see the nozzle orifice, then you can see another orifice right here, and we call that a restrictor orifice. And so this double orifice system, upon which the back pressure pneumatic comparators, they're completely based on this two orifice right there. So what we can see here is we're managing the flow, okay? So the flow that enters the system, again, got to be equal to the amount that escapes through the orifice. So the back pressure pneumatic comparator, here you can see it's in this diagram, is built with two readouts. So balanced system, to reduce the limitations, they start like basic back pressure system. So the flow of air is divided into two channels with two restrictors instead of one. The one is for reference channel and the other one is for zero setting valve. So the measuring channel pressure changes with respect to reference channel pressure in the balance system instrument. So you can see that right here in figure 15.3. So when you take a look at this balance system, you can see the first restrictor, okay, right here. And that's for the reference channel. And the other one restrictor right there, and that's for the zero setting. And we have two gauges right there, master pressure, and the other one is a differential pressure that you can read. And this balance system has fixed amplification, so the only adjustment is zero setting right here. In balance system, they are available in wide selection of amplifications and with relatively wide measuring ranges. So you can see right here the balance system data. So here you have different amplification, discrimination, and the measuring range. Amplification, when you take a look at it, this ratio is pretty easy to read. So every 1 unit you can amplify all the way to 1250, and we have different ratios for amplifications. You already know what discrimination is in the measuring range. So this is your flatness, okay? Here, look at that gauge, and they use a balance system. So the part is placed on the surface plate, okay, and passed over the air jet. The deviation from flatness is then read directly from the instrument dial. Pretty easy to measure. Okay, the next system is rate of flow system. So to compensate for the limitations of your back pressure instruments, we use this. So the constant pressure, rate of flow, or velocity pneumatic comparator, we use them here to compensate the limitations from your back pressure instruments. So in this instrument, the pressure is constant, but a change in the flow rate shows a change in the distance. So distance x right here in this picture, okay? So right over here, this little tiny gap right there. So this is read by the height of a float in a tapered flow meter tube. So when you take a look at it here, you can see the flow meter tube, and that's your float. So in this constant pressure rate of flow air gauge, the conduit pressure, so right here, remains constant. So changes in x right here alter the rate of flow. Okay, so this is read by the height again of the float in a taper flow meter tube. So right here, this little height, and then you can be able to read from your dial the readings. So in pneumatic comparator, the y-axis, this one, is your flow or airflow, and your x-axis is the clearance or distance x between the gauge and the part. And so if we want to draw a graph, we usually give y versus x, okay? You can also go x versus y, the same thing as your clearance versus your flow. Flow versus clearance is a traditional way of calling, but in some textbook, you're going to see they're using it in a reverse way, but it's the same thing. You always know that the y-axis is your flow, and then your x-axis is your clearance, which is your distance x. So yeah, when you take a look at it, the flow changes when the clearance is changed from each point is going different. And a portion of the response curve from B, let's say, to C is nearly straight right here. Okay, and that's telling you that it's suitable for measurement. So the column type flow circuit pneumatic comparator, which is shown right here in figure 15.8. And so this is your features of this metrology, directly provides amplification of more than 50,000 times. That's pretty big amplification. So with additional equipment, that amplification can go all the way to 100,000 times. Okay, this type of instrument is completely free of wear and hysteresis of mechanical system. These are just scripts, and immediately responsive and simple to calibrate. So when you take a look at the features of your pneumatic or air metrology, you're going to see two, your functional or usual metrological features. So when you take a look at it here, no wearing parts, rapid response, remote positioning of gauge heads, cleansing of heads and parts, and no hysteresis, adaptability to their diverse part features, and small size of gauge head. When you take a look at the metrological features, measuring features, there's no direct contact because you're using air. A minimum gauging force, okay, you don't have to put a lot of force in it. Inspection of attribute, so that's go and no-go gauging. All variable, that's your size measurement, you can do that. Range of amplification, pretty good. And adaptability to several modes of measurement, that's your lean position and surface topography. So when you think about the pneumatic metrology features, okay, they recommend air gauging for small holes, highly polished parts, fragile or easily determined parts, remote measurements, and the inspection of multiple part features. So those are what we can do with this instrument. And that's based primarily on the rate of flow type, the one that I showed you in a previous slide, of air gauge with flow meter columns, but many of the features apply to other air gauges as well. So here, let's take a look at the application of pneumatic metrology. So in application, the first step, okay, of this generalized measurement system is called the gauging element. We call it gauging is your first step. So which corresponds to the gauge head for high amplification comparators. And the airflow through the gauging element is proportional to the exit nozzle cross-section and the distance or X distance. So here is your X distance, okay? And these are your nozzle part, and this distance is just showing you the escape area, and that's your part feature, and this is your flow. Again, that's your clearance distance X. And the measurement is going between this flow and the change in this distance. Right now, you're going to have a little bit of trouble trying to understand that, but once you get the equipment, it's pretty easy. Okay, so you don't have to stretch yourself if you don't get it. Right now, just recognize that there's a relationship between the flow and then the clearance, which is your distance X. And our metrology, by using the air in pneumatic measurements, depends on that distance, okay? And we are measuring by using this and then that height or the flow. So there are three gauging elements. The type 1 is the whole beam measure, is the exit nozzle of the gauging element. Type 2 is an air jet that does not contact the part, is the gauging element. Type 3 is the air jet, is mechanically actuated by contact with the part. So single jet nozzles, okay, form the basic gauging element. So these are the examples for the single jet nozzles. So a single air jet, you're going to place that close to the part, and that's going to form the basic gauging element. So when you take a look at it, again, you won't be able to see it. This is just your height gauge, and that's your depth gauge, because we're measuring inside, okay, a depth. This is we're measuring the height. Okay, now you can see it. So right now we're attempting to measure the straightness of a part. Okay, here we're studying the tubing of your straightness. Okay, and here is your squareness. Okay, and this is your squareness again. Okay, so right here you can see your square right there. And then this again is your squareness we're trying to measure. And this one is your outside diameter. Okay, so just go slow and then carefully look and reason. You can see it. Okay, pneumatic gauging, they use spindle. Okay, right here. That's just a cross section so you can see its height. Gauging element in the instrument, especially for the inspection of holes when we want to measure the holes. So the rotation of the spindle can rotate. So when this rotation changes the height of the float. So when it rotates, it's going to change, okay, the height of this float. And if we use a spindle with one jet on one side, the float height is going to rise, okay? So here you can't be able to see it, but know that the float, this one, okay, is going to go up if we use a spindle with one jet, okay, on only one side. Okay, now we're going to use two opposed jets. And we can do, if we use two, differential always come in, okay? So we can do the differential measurement. Why? Because the rotation of that spindle does not change the float height. So when you take a look at it here mathematically, you're going to add A and B, okay? It's going to give you X, let's say just a distance for any position. So therefore the height doesn't change because this is a fix anyway, yeah? So note that if we use the two opposed jets, the float height is not going to change because we're just looking at their differential measurement. So here in this picture, you can see the cross-section of typical spindle for the measurement of inside, again, diameter. So this type is used to determine, again, the roundness and diameter. So every time we attempt to measure something that has a diameter, we're looking at the roundness, okay? Again, you don't have to know the details of the instrument. All you have to understand is every time we attempt to measure the diameter or the roundness, we usually use the cross-section of the spindle, okay, inside of the instrument. So that's all you have to know. And again, we're trying to determine the inside diameter. So to measure average, okay, diameter, we use 3 or 4 jets in different patterns. So you can see right here, when we say jet, okay, that's our single jet, because we have only one. Okay, it just looks like a little thing right there. And so single jet is going to plot check, okay, concentricity, location, squareness, flatness, straightness, length, and depth. So what's trying to show you right here is, you know, by with a simple change of the spindle, that's your spindle, and we're changing the jet in the spindle. A variety of characteristics may be checked. So second, here two jet. So we're going to check inside diameter, out of round, bell, mouth, and taper. 3 jets. We can check the triangular, out of round, and 4 jets. Okay, and we're going to use this type to furnish average diameter readings. 6 jets. It's going to show average, okay, determinations for both 2 jets here and 3 jets condition. Again, what are we designing? We're playing with the airflow, okay, through that spindle. And we usually use a mirror, okay, to check the back side of the spindle for squareness and straightness. lack of squareness can create fluctuation for the float height, but if the axis of the hole is square to the shoulder, the spindle does not alter the height of the float. So when we look at the diagram, okay, for the instrument, so we see if the axis of the hole is square to the shoulder, is completely square, okay, to the shoulder. Rotating this spindle in your instrument is not going to alter, okay, the height of that float. So that's right here, you can see, okay, we're checking again for the squareness, okay, so it's when you look at it here for A and B, so if you measure the squareness and if they are square, you can see the float is not going to change in height. A lack of squareness, you see it's messed up around here. The shape is totally different from here. So at that time, you can be able to see the float. See? Fluctuations. Okay? So that's showing you the lack of squareness. If you can see the fluctuation float height, okay, in your instrument. So that's how we measure the squareness. So pretty easy, huh? Okay, spindle also checks the hole straightness. So rotating the spindle from A to B does not change the combined clearances, your X distance. So if the hole is straight. If the hole isn't straight, see, you can see some curves right there. Here, perfectly straight. So if the hole isn't straight, okay, you will have a maximum and a minimum reading in your instrument. Surface finish. So pneumatic comparators, they provide, again, no metal to metal contact. So the type 2 pneumatic comparators, they provide high amplification, high sensitivity, fast response, good accuracy, and also other benefits. And it has a smaller range in electronic instruments, but air gauges, they provide superior resolution, so which leads to exceptional readability. So don't get into so details. All you have to understand is for surface finish. Okay, type 2 is pretty good because they have very high amplification. So with type 2, the reference line, okay, is the reference line, the pitch line, we call that, and that's between the crests and the valleys of the surface. So when you take a look at this diagram right here, then that's your pitch line. And we have, every time we say the clearance, okay, we're talking about the distance. So that's your major clearance, okay? And this is your minor clearance. Why this is major? Because we are going with this pitched line in between the crests and then the valleys right there. And that's your part surface that we're trying to measure. So if you take a look at it here, your x distance is going to go from the pitched line, okay, all the way to the end of your minor clearance. Again, you don't have to go into details. All you have to know is a general knowledge, okay, about pneumatic metrology. So for surface finish, type 2 is good. Why? Because it has high amplification. And for type 2, we go by the pitch line. That's your reference line. Where is the pitch line? The pitch line is between the crests and the valleys. And that's all you need to know now. In this table, just trying to show you the selection gauging elements. So we have type 1, 2, 3. Which one are you going to use? We list the operation and measurement for you. So for type 1, part formed of exit nozzle, and we can measure the cross-sectional area. So if you want to go for cross-sectional area, you choose type 1. Type 2, high amplification 1, tolerance is not greater than 0.075 mm, so that's 0.003 inches in British system on parts with surface finishes, okay, about 65 microinches or finer. Too much information here. All you have to know is we can go high amplification, okay, with type 2. So go for it. When you look at the operation, it's just a clearance, again, between the part and your nozzle of your instrument. Type 3, mechanical contact, okay, which regulates flow. So when you take a look at it here, about the same, okay. Part with surface finish is rougher than 65 microinches. This one we can go finer, therefore it has higher amplification. Or parts whose surface finish differs from the master by 50 microinches or more. And that's how, based on this information, we select type 1, 2, 3 gauging elements, okay, for our measurement purposes. So when we think about porous surface, narrow lens, or mouth of hole, for these situations, okay, we use type 3. Why? Because you can provide the metal to metal contact, okay, and we don't use type 2 here, even if it can offer you finer amplification, but this type 3 is not so bad as well, okay. And for this situation, again, we prefer a variety, okay, we prefer type 3 for a variety of situations like this. Porous, narrow lens, and mouth of hole. In inspection procedures, type 3 gauging elements can be used simultaneously. So what are we doing? We check the length, the width, the thickness, and the taper, and we can do all of that at the same time. So when you take a look at it here, it looks like a little typewriter, but it's not a typewriter. It's just showing you the vertical flow tubes, okay, of our pneumatic comparators, particularly suit them for multiple inspection setup. So we can do 1 all the way to 10 right there. So either type 2 or 3, okay, gauging elements, you can use one of them. So here you can see your length, width, thickness, and taper, okay, dimensioning, and we're checking all of that dimensions, and we're doing it simultaneously, okay, and we're using 10 of type 3 gauging elements, okay, so that's pretty cool and convenient for doing inspection at the same time. Okay, mastering the pneumatic comparator. How do we do it? So to master this instrument, so the instrument must be set up, and we're going to use 3 steps. So the very first one is set the instrument. to a master at the high or low, and then adjust the amplification, and then set the instrument to a master at the second limit. You can't be able to understand it here because we definitely need the instrument to do these steps. So all we have to know is if we want to use the pneumatic comparator, we got to be sure we do the setup correctly. And we're going to do that 3 steps to make sure our setup is correct. So we can use this comparator in the right way. And it will give you a reliable measurement. Advantages of pneumatic comparators. So a typical rate of flow type comparators, they use simple circuits. So therefore that's the advantage. And adjustments. In most of the instrument, if your circuits are simple, that's an advantage. If you can be able to do simple adjustment, that is also an advantage because nobody want to use a complicated instrument. You want something simple so you can set up quickly and be able to measure. You also want something that is easy to read. So those types of instruments are good and popular. Again, numeric comparators are popular because it's really easy to use. So here we're getting into the discrimination, so your scale and the range of several amplifications. So the scale length is no longer than other instruments with similar amplifications, and they provide exceptional reliability. So tolerances are spread over this great scale length, so the instruments minimize the observational error. So again, you can minimize the observational error if you have your tolerance spread over the scale length. And again, don't confuse yourself or stress out. It's just trying to tell you if you use the pneumatic comparators, tolerances can be spread over great scale lengths. So therefore, we can minimize the observational error. That's all. Yeah. So when you take a look at it here, this blue area right there, and we call that spread, right? Tolerance spread. Okay. Reading the pneumatic comparators. A variety of scale and pneumatic comparator comes in different style and with different amplification. So here in this picture, you can see the scale with 2000 time amplification. And the same discrimination, it's going at our usual 0.0001 inches. External and internal are just showing you these are all 2000 times scales, all of them, and similar ones available for higher amplifications, and they are printed on both sides, and they are changed easily. So you can see printed on both sides. So the first one is A and B, this scale right there, and that's a zero center. So see how they're all aligned? That's your zero center. Now the second, C and D, that's your standard right hand. And you have your C, and that's your external, and then your D is your internal. So when you look at it, you can see like that. It's completely opposite. See how it's going. The plus is on this side. Yeah, a little bit. It will make you dizzy to look at. Okay, E and F. Again, your external. And then this is your internal. And your G and H is your top 0. Here, the same thing. 1 and then 2. And then your 3. And if you look at it here, that's your plus and that's your minus. Flip. You can see the plus is right there, and the minus is on this side, see? And we call that the top zero. Why? The zero is now on the top of the scale instead of like this, yeah? So make sure you know where the plus is. So when you take a look at the picture, go slowly, okay, and try to find where the pluses are. Otherwise, you can't be able to see it. Anyway, we're not getting into details. All you have to understand right here is reading the pneumatic comparator. And we have a variety of scale, okay? They all come in different style and amplification. Usually we go with 2000 times amplification and with discrimination of again 0.0001 inches. Okay, a common term that you have to know if you use your pneumatic comparator. So in this measurement we use a term come up, and we call it a come up when the element approaches the part tolerance. Okay, so when you take a look at it here, that's a come up. And we call it go beyond when the part exceeds the tolerance. So here this, okay, is your part tolerance, and that is your range. So coming up, we're approaching to the part tolerance. We go blah 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 blah, and then if you pass that, okay, exceed the tolerance, we call that go beyond. And this is your measurement point. Again, you're dealing with a float, okay? So it's like floating up in the part tolerance, and then you go beyond. That's why we call it coming up. The float is coming up, now in the part tolerance, and then it goes beyond. Yeah. And these two terms again, come up and go beyond, we only use in this air pressure instruments, pneumatic comparators. Okay, the sign of the measurement value is reverse for inside and outside measurement. Why? Because separate scales are needed for internal and external measurement, so you can differentiate them. And because the relationship of your flow rate and the plus minus sign is reversed. So for internal measurement, large flow is a plus. Okay. For internal measurement, a small flow is a minus. So how do we know the large flow? Because it flowed up, see? And that's a plus. Here, see the float is so low, and that's a minus. For external measurement, the large flow floating up, okay, is a minus. And the small flow floating down, okay, it's not going up a lot, actually. And that's your plus. Okay, scale selection. So the rule to select the scale, which one are we going to use, is to choose the most sensitive one. Why? Because that is going to contain the tolerance of the dimension to be measured entirely. So for example, a grinding operation is going to require you 0.0002 inches tolerance in different spread. So when you take a look at it here, this is your power, your amplification, and here is your tolerance spread, okay, in inches. So 0.2, 4, 1, 2, and 4. So what we're seeing here is the effect of amplification, okay, on the tolerance spread. And we have 1, 2, 3, 4, 5 scales. And each one of them is 0.0002 inches, okay? So point out here, 2 of them. Here, 1, 2, 3, 4 of them. And then so and so. So that's 4, and that's 2 inches, and that's 1 inches, and that's 0.4, and then this is 0.2. So you can see the more your amplification going up, okay, the spread is larger. So most of the scale is outside the tolerance. So by using this top 0 scale, we increase the amount of scale below the tolerance. And the long come up range, okay, which let the operator follows the progress of the cut. So you can't really see it right now by reading it. And what's trying to tell you is the long come up range speeds the grinding operation. Okay, so if your grinding is speeding up, when you take a look at the measurement, you're going to see a long come up. Okay, so here is our part tolerance, and our float is going up, and this is what we call a come up. Okay, and that range is approaching 0.0015 here, and that's a part tolerance. Okay, the next one is your top 0 spindle technique. So in this technique, we use spindles with greater than usual clearance, your X distance. So special gauging elements and scales compensate for this change because they are used to modify operations to provide maximum come-up range. Okay, we want the maximum come-up to provide additional wear life or provide an optimum combination of these. So when you take a look at it here, the special gauging elements and scales, again, they are available to modify operation, okay, in A in order to provide maximum come-up range right here in B, to provide additional wear life here in C, and then also to provide an optimum combination of them in D. So you gotta go slowly to take a look at it here. Okay, so this is our come up right there, and that's our part tolerance, and we're not using this, and that's our conventional processing. So when we start to use the top 0 processing or top 0 spindle technique, you're gonna get, okay, a long come up. Okay, so that's the first thing we see when we change the technique. Okay, so that's your maximum come up range. So that's your part tolerance. And we're going to continue that, and you will see you have additional wear life. So that's a 0.0015. Okay, and that's your normal wear life and approach. Why do we get this? Because, okay, this approach is giving you a maximum come up range. Okay, and that's the reason why you have additional wear life right there. So when you add them up, you have additional approach, and then you have additional wear life, okay, which is better than your normal wear life and approach. Don't worry about the values, okay? I don't think you can be able to see it right now. So just go by changing the method. We get a long come up. If you can get this, I'll be very happy, okay? Okay, this is very important, just showing you some reason for the pneumatic inspection of small holes. And when you take a look at this table, you're going to see the gauging elements can be very small. Okay, why do we use the pneumatic inspection for small holes? Because they're small. And that's going to allow us the precision measurement of smaller inside diameters than is possibly by using other measurements, other means of measurements. Deeper holes, you can go that, okay, by using the pneumatic inspection. You can inspect the deeper holes because the depth has little effect, okay, on each measurement. Greater accuracy, you can get it because rocking and centralizing, okay, are important in this instrument. Nominal gauging force is going to allow you thin-walled and yielding materials to be measured. What you have to know right here is the gauging force is not big, okay, so that's pretty good. to measure small holes. Absence of metal-to-metal contact is going to protect the finely finished surfaces. Okay? Because metal-to-metal contact definitely give you friction, so remember the friction, and that's not good. Okay, for finished surfaces that are totally finely constructed. So in order to protect that, measuring the small holes, we use pneumatic inspection, meaning that we use air instrument. The last one is your metrological data for your pneumatic comparators. It's just showing you, okay, your reliability right here. And then you have your different instruments right there with the different amplifications, okay, your power X or your amplification right there. And it's just showing you right here your type of measurement, and they're all comparators. So yeah, pneumatic comparators, so everything is comparison here. They give you your normal range, design precision, discrimination, sensitivity, linearity, and these are your reliability. Okay? So don't worry too much about it. I just trying to tell you different amplification is going to give you different reliability, sensitivity, linearity, and discrimination. If you can get that, it's alright. Okay, so that's the end of chapter 15.